Hello, this is Team 35 and using deep learning to improve diagnostic capacity for X-rays. We're going to speak a bit about our problem first, followed by a literature review, experimental setup, approach, a quick demonstration on my local computer, followed by evaluation, conclusion, and future work. In terms of our problem, there's 3.5 billion medical examinations per year, with chest X-rays being the most common. Well, we'd like to help a doctor reduce their workload by focusing on minimizing false negatives and improving the accuracy of diagnoses with the ChestXray dataset. Our problem domain consists of 224,000 chest X-rays and 65,000 patients collected from Stanford Hospital between 2002 and 2017. Each of these pictures was labeled for the presence of 14 different diseases. In terms of our literature review, we'd like to point out that Raj Pukar was able to create a 121-layer convolutional neural network, which was very successful. And we'd like to show that the FAM model, which is the state-of-the-art model, was able to receive an area under the curve of 0.94 on predicting 5 selected pathologies. Our experimental setup is as follows. In terms of the data, there are, again, 224,000 images and 65,000 patients that were split up into the below sort of demographics. And our software stack was created using Pillow, PySpark, NumPy, Petastorm for data retrieval and storage, and we used a distributed file system, HDFS, as well as had PyTorch for our learning modules and included Docker for our containers and deployments, building on top of the SunLab big box Docker container that we use in class. Our hardware specifications basically focus on the fact that we were able to find a Google Compute Engine virtual machine, which is very highly powered and very good for this type of learning. Our approach was split into data training and data processing, with the primary goal of reducing false negative rates and false positive rates. The architecture of exactly what we would put into our virtual machine is as follows. We'd have a Docker container and data. We'd load it into our ETL, output a file into our distributed file system, load that into our trainer, had to create an intermediary H5 file, and then loaded that H5 file and then created the models. Now this intermediary H5 file was required because otherwise we found we'd run out of memory and our trainer would get killed with out-of-memory errors. Our data processing included image processing, writing the data as NumPy arrays, and saving files to a distributed file system. Our learning included choosing DenseNet 121 and improving that model, adding dropout layers, batch normal layers, as well as improving the performance of our training by reducing the number of trainable parameters. Here's a visual representation of our improvements for the DenseNet and learning. And now I'll give you a quick demonstration on my local machine of our script running. Hi, so just a quick demonstration on my local computer. I've gone to our GitHub repo, and basically I've already built our Docker containers and have started our services, which creates the HDFS nodes for our distributed file system, and also entered into our Conda environment. Now all I need to do is go into our ETL folder and run our Petastorm ETL. Now what this does is it takes in those local images and using PySpark distributes those images and does a little bit of image processing on those images and creates a Apache Parquet file with some Petastorm metadata. Eventually, we're going to be able to read in that Petastorm data into our deep learning algorithm and then use that in our training. So it's just finished now. I'll be able to go into our deep learning folder and then run our script, which will take that Petastorm data and it actually generates an intermediary HDF5 file and then loads that HDF5 file into a trainer in order to start manipulating and learning from the images. We found that we needed this intermediary file because otherwise we'd run out of memory just because of how the data was loaded. And as you can see, you get some initial results here. And so here are our results. Typically our lesion, lung lesion and pleural other accuracy was quite high. Our fracture accuracy was quite high, although in our validation set we didn't have any actual fractures, so our confusion matrix looks a bit confusing on that one. But importantly, consolidation and no finding in particular is is what we would like to focus on, where it's actually quite high in terms of our accuracy, reaching almost 0.90. The challenges that we faced were quite a few. It was quite infeasible to develop locally. The iteration cycles were quite slow, and we kept on running into memory and storage limits, even on just the 11 gigabyte images. The initial ETL was not distributed in order to get a proof of concept working, but we were able to eventually figure that out. However, we kept on running into a lot of these memory errors, and we've tried several different methods for data storage and loading, including NumPy, HDF5, Petastorm, and pickling. We tried adding additional synthetic images by rotating the images in order to improve classification and reduce rotational invariance on CNN models, but we ended up hitting a problem with memory storage. So in conclusion, we were encouraged by the accuracy of 0.914 for the no finding, which we found in our original proof of concept, but we had to give up a little bit of that accuracy for performance in our final model. There were also going to be some challenges to adoption, including that it might take a while for doctors to accept ML algorithms, the anxiety of job losses for doctors, and anxiety and liability of missed diagnoses. However, we do think that the ML can really augment a doctor's toolkit in addition to the current methods. Our future work will try to focus on causal relationships between diseases to build hierarchical model label classifiers, applying techniques like data augmentation or stratified sampling, and image processing using template matching algorithms to mitigate the issue of noisy images. I'd also like to explore different models and other parameters to boost accuracy and area under the curve. Here are our resources if you would like.